All right, here we go. 3. Boom, and we're live. How are you, sir?
I'm fine, pretty good.
Thank you for doing this. I appreciate it.
That's fine, my pleasure.
Who roped you into this?
Well, I suppose James Tagg probably.
I'm a big fan of your work. I've read much of your work. I've seen many of your interviews and videos online. And one of the things that I really wanted to talk to you about that I find quite interesting is consciousness. And your belief that consciousness is not simply calculation, but that there's something more to it, and what you think this more could possibly be from a scientific perspective, which is unusual because a lot of people have some theories about consciousness, but they're usually crazy people like myself.
Well, I mean, we're all conscious, and so we may have theories about it.
Yeah.
But no, the ideas came by a somewhat roundabout route. I went to Cambridge to do graduate work. It was mathematics. I was working on pure mathematical subjects, algebraic geometry. But I thought, we got 3 years. I'll spend some of the time going to other talks that might be interesting. So I went to 3 talks particularly, which had a big influence on me. One was a talk by Herman Bondi, on general relativity, cosmology. Wonderful talk with very sort of animated presentation he had. And then there was a talk by Paul Dirac, one of the founders of quantum mechanics. And his talk, his complete wonderful talk too, wonderful lectures as well, but in a completely different style. He was very quiet and precise in what he said and everything. Anyway, in the very first lecture, he was talking about the superposition principle in quantum mechanics. So if you have a particle, and it could be in one spot, or it could be in another spot, then you have all sorts of states where it can be in both places at once. And that's sort of strange, but you've got to get used to that idea. And he illustrated with his piece of chalk, and I think he broke it in 2 to illustrate it could be in one spot or in the other. And my mind sort of wandered at that point. I don't know what I was thinking about, but I wasn't concentrating. And about a few minutes later, he'd finished his description, his explanation, and I had some vague memory of something about energy, but I didn't understand what he said, and I've been totally mystified by this ever since. So I suppose if I'd heard what he said, he would have said something to calm me down and sort of accept it in one way or another. But as it was, it seemed to me this was a major issue. How on earth do you have things that don't behave according to what quantum mechanics says, like cricket balls and baseballs and things like that? Anyway, that's 2 of the talks. The other course was a course by a man called Steen, who talked on mathematical logic. And he explained things like Gödel's theorem and Turing machines being the mathematical notion upon which modern computers are based, or all computers basically. And the thing about Gödel's theorem, you see, I used to have a colleague when I was at undergraduate, Ian Percival, who also became a scientist later on, and we talked about logic and how you could make these kind of mathematical systems which worked out logic. And I'd heard about this Gödel's theorem, which seemed to say that there were things in mathematics that you just couldn't prove. And I didn't like that idea. But when I went to this course by Steen, and he explained what it really says. And what it says is, suppose you've got a method of proving things in mathematics. And when I say things, I mean things with numbers. The one famous example is Fermat's last theorem. There's the Goldbach conjecture, which isn't yet proved, that every even number bigger than 2 is the sum of 2 prime numbers. That's the sort of example of the thing. It's just sort of mathematical things about numbers, which you can see what they mean, but it may be very difficult to see whether it's true or untrue. But the idea often is in mathematics, you've got a system of methods of proof. And the key thing about these methods of proof is that you can have a computer check whether you've done it right. So these rules, they could be adding A and B, it's the same as B and A and things like that. And if you give you say to the computer, say, here is a theorem, like Goldbach conjecture, and you see whether it can be proved, and you say, maybe I got a proof, and this follows these steps, and you give it to the computer, and it says, yep, you've done it right, it's true. Or maybe it would say, you've done it right, and it's not true. Or it may not say anything, it might just go on forever. But these are the sort of outcomes. And the point about it is that if you believe that these procedures do give you a proof, in other words, that if the algorithm says, yeah, it's true, then you believe that it is true because you've understood all the rules. You looked at the first one and said, yeah, that's okay. You looked at the second one and said, yeah, I see. Okay, that's great. And you go all the way down. And as long as you're convinced all those rules work, then if it says yes, that's something you believe. Okay. Now what Gödel shows is he constructs a very specific sentence, a statement, which is a number thing, like the Fermat's theorem or something, a thing about numbers, which what he shows is if you trust this algorithm for proving mathematical things, then you can see by the way it's constructed that it's true. But you can also see, by the way it's constructed, that it cannot be proved by this procedure. Now, this was amazing to me because it tells me that, okay, you cannot formalize your understanding in a scheme which you could put on a computer. You see, this statement which Gödel comes up with is something you can see on the basis of the same understanding that allows you to trust the rules, that it's true, but that it's not actually derivable by the rules. You see it's true by virtue of your belief in the rules. And this to me was amazing. And I thought, golly, what's understanding? What does it mean? Is it something following rules? Is it an algorithm? Well, this more or less says it's not an algorithm, because whatever it was, there would be something that you could still see is true, even though you don't get it through the algorithm that you had in the first place. So this was there are a lot of subtleties about this too, which people argue about endlessly. But it was pretty convincing to me that this shows that we don't think, when we understand something, that what's going on in our heads is not an algorithm. It's not following rules. It's something else. It's something that requires our conscious appreciation of what we're thinking about. Thinking is a conscious thing, and understanding is a conscious activity. So I formed the view that conscious activities, whatever they are, not just that kind of thing, but playing music or falling in love or whatever these things might be, are not computations. There's something else going on. And then I thought, because I like to think myself as a scientist, and I think that what's going in our heads is according to the laws of physics, and these laws of physics pretty good. They seem to work well in the outside world, and so I believe that the laws that work in our heads are the same as those laws. So I began to think about it. Well, what about Newton's mechanics? Well, you could put that on a computer. What about Einstein's special relativity? You could do that. What about Maxwell's wonderful equations, which tell you how electricity and magnetism operate, and light and radio waves and all these things? That all follows this beautiful set of equations that Maxwell produced. You can put that on a computer. Okay, you may have to worry about approximations, and these depend on continuous numbers rather than discrete things, but I didn't think that's the answer. Then I thought, what about general relativity, Einstein's theory of gravity with curved space and all that? Well, we're familiar now with LIGO, this detector which has detected black holes spiraling into each other from distant galaxy. And how do we know that those signals are black holes? Well, because of calculations. People have put this thing on an algorithm, and you know what those signals look like. So Einstein's general relativity, sure, you can put that on a computer. What about quantum mechanics? Well, there's the famous equation of Schrödinger, which tells you how a quantum state evolves. You could put that on a computer too. It's difficult in many ways. There's many more parameters you've got to worry about. But it's just as computable as these other things. Well, you see, I then remembered Dirac's lecture, you see, and how it is that these things that work in the quantum world don't seem to work at the level of classical big things. And it all depends on this process of what's called measurement in quantum mechanics. And the measurement process is something you learn how to do, but it's not the Schrödinger equation. It's something else. And Schrödinger himself was very intrigued by this fact, that his own equation gives you nonsense. And the famous Schrödinger's cat, where he produces a situation in which the cat would be dead and alive at the same time, he produced that in example simply to demonstrate that, roughly speaking, his equation gives you nonsense under these circumstances. So there's something else. And the something else goes beyond our current quantum mechanics, and it tells you what happens when the quantum state makes a decision between, well, it doesn't follow the Schrödinger equation, it does one thing or the other. Now, everybody knows that who does quantum mechanics, but they think, oh, it's what's called making a measurement and you're allowed to do something different. But that didn't make sense to me. And so I had the view that, okay, there is a big gap in our understanding. And if there's something in the world which isn't something you could put on a computer, that's where it is. So the view, I've held that for a long time, and that there's something non-computable, something beyond computation involved in our understandings of things. So that's a view I held for ages. I didn't do much with it, I just held the view. Until I think there was a radio talk between Marvin Minsky and Edward Fredkin, and they were explaining about what computers can do. And they were talking about, okay, you have a computer, two computers talking to each other over there, and you walk up to the room, and the time you've walked up the room to the computers, they have communicated with each other more thoughts than the human race ever has done, you see. And I thought, well, I see where you're coming from, but I don't think that's what's happening. In human communication, human understanding is something different from what computers do. And consciousness is the key thing. Consciousness is something different from computation. So I've held that view, but then when I heard this talk by Minsky and Fredkin, I thought, well, I had ideas of writing a book sometime, a long time in the future when I'm retired. This was some while back, I say. And I thought, well, this gives it a focus. And so I wrote this book called The Emperor's New Mind, which was supposed to be saying, well, everybody seems to be thinking one thing, but the little kid notices that the emperor doesn't have any clothes. So it was that theme of that story, which was the basis of the book. So I say, okay, maybe lots of people think that all we're doing is computing, but if you stand back and you say, well, no, there's something else going on. So that was the basis of my thoughts about consciousness. But I wrote this book thinking that by the time I got to the end of the book, you see, it was mostly about physics and mathematics and things like that, but I was really aiming for this thing about what's going on in conscious thinking. And I thought, well, I'll learn a bit about neurophysiology and so on, and by the time I get to the end of the book, I'll know pretty well what it could be. I didn't. I got to the end of the book, and I just sort of tapered off rather with something a little bit unbelievable, and that was the end. Now, you see, I'd hoped that this book would stimulate young people to get interested in science and that sort of thing, that mathematics, and that was fine. And when the book was published, I didn't get letters from young kids. I got letters from old retired people, the ones who'd had the time to read my book. Okay, well, that was a little disappointing, but okay, I'm glad the old retired people liked my book. But the other thing was, I got a letter from Stuart Hameroff, and this letter said, more or less, I think you don't appreciate that there's something else going on, not neurons. I mean, the neurons, I could see you couldn't isolate the quantum effects, and you get what's called environmental decoherence would happen, and you get no way of keeping the quantum state to the level that you need in this picture. So I realized I didn't have it. But Stuart Hameroff pointed out to me these little things called microtubules, and he'd built up a theory that microtubules were absolutely fundamental to consciousness. He had his own reasons for believing that. I'd never heard of them at that time, but then I checked up. I get lots of letters from people who maybe don't make sense sometimes, the letters. And this one, I thought, well, is this another one? But then I realized these microtubules are there, and they look like just the kind of thing that could well be supporting the kind of level of quantum mechanics up to a level where you could expect the quantum state to sort of collapse. That's the terminology people use in quantum mechanics.
And microtubules, they are inside brain neurons?
They are indeed.
And this is a recent discovery, fairly
no,
recent?
No, it's been going on for... They're actually in lots of cells, you see. People often complain, oh, they're in your liver too, not just your brain, so why isn't your liver conscious and all that? But this has to do with the organization of them and the nature of them, the particular kind of microtubules, how they're arranged, which is different in the brain.
How does it vary in the brain compared to other cells?
I think one big difference, although not Stuart emphasizes this so much, there are two kinds of microtubules. They're the ones called the A lattice and the B lattice. And the A lattice ones are the very symmetrical ones. They're tubes and they look the same all the way around. They've got a very beautiful arrangement of these proteins called tubulin, and they make a very nice arrangement, which is connected with Fibonacci numbers and things like that. So they look a bit like fir cones, but they're all parallel. They don't taper off. But the thing is, in the brain, I think most microtubules are probably what are called B-lattice ones, and they don't have so much symmetry. They've got a sort of seam down the one side, and they're very important in transporting substances around cells and so on. And microtubules, all sorts of things. They don't just do what Stuart and I think they may be doing in the brain. So the idea is that in the brain, they're organized differently, and probably the ones that are important are the A-lattice ones, which are the very symmetrical ones. And for a long time, people couldn't see the difference because they look very similar. And they may well be the ones that happen to be in pyramidal cells as a particular kind of cell. So, one of the things that interested me a lot is how it is that not all parts of the brain are the same in this respect. You see, you've got the cerebellum. This is the part at the top, and divided down the middle. And that, when you see brains, that's what you normally see with the convolutions in it. But right underneath and at the back, there's a thing called the cerebellum, which looks more like a ball of wool or something. And the cerebellum, there may still be argument about this, but it seems to be that it's completely unconscious. And it has comparable number of neurons, far more connections between neurons than the cerebrum. And it's what takes control when you're driving your car and you're thinking about something else and you're not thinking what you're doing, because it's unconscious. And the unconscious control, a pianist who's very expert and moves the fingers around and plays a note with a little finger, that pianist doesn't think, well, I've got to move that muscle this way and this bone that way and so on, and it's all controlled unconsciously. And a lot of this unconscious control is done somewhere else in the cerebellum when you get really skilled. So it seemed to me, okay, you've got different kinds of structures, and it could well be that these pyramidal cells, which have a particular organization of microtubules, are the ones where the consciousness is really coming to light mainly. I don't know. There's a lot which is not known about this, controversial and all sorts of things. But the cerebellum seems to be different and organized differently. So it's not just how many neurons, how many connections are there, because there are more in the cerebellum. So it's not that, it's something else.
Do they know this from observing the brain through fMRI or something like that during particular activities?
I don't know. I would imagine partly just examining it from dead people and looking at brains and trying to estimate how many neurons there are in it.
Right, but how would they know which portions
which
are
is
active
conscious
during particular activities?
I don't know that they do know that well, I guess. But the cerebellum, there is a bit of an argument about that. I think whether it's completely unconscious or not. But it seems that actions that are carried out by the cerebellum, you're not aware of what you're doing. But I mean, it's, if you're a tennis player who has to think very carefully about what way to tilt the ball. Now, the control of what you're doing, so overall control, is probably done with the cerebrum. But the cerebellum is controlling the detailed motions, how the fingers move and all that kind of thing. And then you make sure that the player thinks he's going to hit the ball down the line there, and then the rest is done under the control of an unconscious procedure. I mean, I may be simplifying, but
I understand what you're saying. So you're saying that we don't totally understand, but we know that there's different parts of the brain that are responsible for different activities, and some activities don't seem to be conscious.
Yes. I mean, I think it's probably the case. No, I don't know. I shouldn't make a statement. I don't really know. But certainly there are lots of different parts of the cerebrum which maybe not conscious too. So I'm not saying that the whole thing is capable of being conscious. There seem to be differences in different parts.
But are you convinced that microtubules are responsible for consciousness, or it's a primary theory?
I think they're one of the best candidates. You see, I don't think it's only microtubules. I don't know. I'm not sure what Stuart Hameroff's view on this is. He certainly thinks the microtubules are exceedingly important in consciousness, and I think he's right. That's the feeling I get. And he's done a lot of work on trying to find what anesthetic gas is. It's one of the important ways you can tell things about consciousness. Most of it you can't. It's just hearsay and whatever it is. But one of the important ways you can tell something about consciousness is what turns it off in a reversible way. In Stuart's job is he's an anesthesiologist. He puts people to sleep. Well, I think he would complain if I say putting it to sleep, because under anesthetic is actually different from sleep. But you make them unconscious in a reversible way. You want to make sure that you can wake them up again. And it's obviously a very skilled thing. But I guess a lot of his colleagues might be skilled at doing it, but don't ask the questions about what they're actually doing from the point of view of the biology and the physics and so on. So Stuart was really interested in that question. Partly, I think, things like mitosis, cell division, and he was very struck by the way that the chromosomes all line up, and that there's these microtubules which are pulling them, and they're a really big part in the structure of cells and how they behave and so on. But why their consciousness? Well, I guess it was his experience with putting people under anesthetics, and the fact that the gases which put you to sleep, and they're, again, I shouldn't say to sleep, but put you under anesthetic, are very unconnected chemically. They're different kinds of things, but yet they still seem to have the same effect. And to understand what it is that they affect is, that's a lot of his interest is to do with that.
So just by putting someone unconscious and registering what parts of the brain are no longer active, this is what they're using to sort of reverse engineer by turning those parts on. That's what enables consciousness? Is this the... Well,
I think it's probably a simplification of what's going on. But that's a good first step, yes.
Consciousness becomes, as a subject, it's very susceptible to woo, right?
Indeed.
It's one of those weird ones where people want to start talking about souls and universal consciousness, and it's
a murky area.
Yes.
And there's no clear borderline. Well, you see, Stuart runs these consciousness conferences, and he's very broad-minded. He has people all sorts of different views like the ones you mentioned. And it's not necessarily his view, but he likes to get a broad perspective on what's going on. I'm a bit more narrow-minded than he is on these matters.
Yeah, I am too. I'm very skeptical because I understand the inclination that people have to lean towards the woo, that it's very fun.
Yes.
It's, for whatever reason, people are inclined to lean towards... You saw that movie? I don't know if you saw it. What the bleep do we know?
Oh yes, I did.
People love that kind of stuff.
That was a little worrying to me.
Little bit.
yes, indeed. No, that did worry me.
Yeah. Well, it's just it was written. The movie was made by a cult leader.
Yeah.
And it gets a little squirrely, right?
You're absolutely right. And I was distinctly worried by that movie.
I'm sure you were. A lot of people that I know that were like yourself were worried.
Yeah.
But this is something that everyone contemplates. Like, what makes you conscious?
Yes.
What is the soul? Is it a real thing? What is your consciousness? Is it simply just your own biology trying to calculate your environment and looking out for its best interests and trying to procreate and move forward with the genes that it has? Or is it something almost mystical? Or far more complicated, maybe even. Instead of the word mystical might be tainted, maybe something far more complex than we're currently able to understand.
I think to some extent I would agree it is, because it's certainly different. I mean, to have some internal perception of the external world and being able to think abstractly and all these things, it's surely different from the way a baseball runs through the air and what makes it spin.
And different than every other conscious animal.
I'm not so sure about that.
No?
I think the difference isn't that big.
Really?
I mean, okay, we use language to a degree. I mean, some animals use language to some kind of degree. There's a huge difference in degree. I'd agree with that. But whether it's a difference in kind, I'm not at all sure. You watch these nature movies, and I remember seeing one about elephants, and this was about how the elephants were. They're always led by a female elephant, and that's not relevant to the story. But they were trying to go from A to B. I don't remember what it was, and there was a whole herd of them. They would be doing that. But then at a certain point, they made a detour, and they went off to a place where the leader of the elephant herd, her sister, had died, and the bones and the tusks, I suppose, were there. The bones, anyway, were there, and the elephants picked them up, handed them around, and seemed to caress them and move them around, and then they went back to join to the route that they were at before. Now, what does that tell us? There's something going on which is not just some machine behaving like a robot. There's some feelings there that we can appreciate. I mean, another one I remember was one with these African hunting dogs, and the dogs. You see, there was a route where some antelopes would tend to go, and they had to go across the river. And when they got to the point where they crossed the river, they might slow down and make their way to get across. Now, these hunting dogs, you could see them. I think it was taken from the air, and they would go along towards this place where the river was, and then they would break into two. So half of them would go one way and they would hide just where the river starts. And the other half would go and chase the antelopes. They'd go and bark and make an awful noise, chase them right there. And then the other ones would pounce on them. I mean, there's something there which is, they've been working it out between themselves, how to do it.
Yes.
Communication of some kind.
Yes.
And I think there's what you call understanding, okay, at a more primitive level than in human understanding, but nevertheless, there is something, there's no sort of clean dividing line in my view. It's pretty continuous.
Yeah, and this exists in wolves as well, very, very similar behavior. And they do seem to have not just verbal but nonverbal communication. They seem to have some understanding of what the task is and what their roles are in the task. And even though there's not as many variables maybe as human life, there definitely seems to be a conscious awareness of, first of all, their position in the hierarchy of the tribe, of the pack, rather, but also what their objective is. This is not a selfish objective; it's a group objective, and they operate as a group, and they do move like those African dogs that you were talking about.
Yeah, no, it's fascinating all that. Yeah, and there's a lot of indication that, certainly chimps and elephants and things and dolphins, we know about them, but I imagine it goes quite far down, I should think.
How much have you studied octopi?
They're fascinating, aren't they? Yes. No, I haven't. There's a new book about them, which I haven't got the chance to read yet. I want to read it. I think they're highly intelligent.
Yes. Yeah, I've only been really paying attention to them for a few years. I have a good friend. My friend Remy Warren was doing a television show called Apex Predator, where he studied the way different animals hunted. And he started studying the way octopus and cuttlefish and all these different different octopi and the way they could adapt to their environment by changing their actual, not just the look, but the texture of their skin instantaneously. And how this is not really understood, not only how they do it, but how they know what's below them, what they're copying.
Yes.
That they somehow or another can figure out how to blend in almost perfectly with their environment.
It's amazing, isn't it? Yes.
They also can open jars and they can climb out of tanks. There was one guy had a camera on his tank because he had two tanks, and one of them had very expensive tropical fish and the other one had his octopus. And he was trying to figure out what was happening to his expensive tropical fish, so he put a camera on it. and the octopus was climbing out of the tank, walking across the ground, climbing into the other tank, killing one of the fish, eating it, and then going back into his tank.
Yes. Yeah,
that's heavy.
Indeed. Well, there's one I saw about I think I heard the description, or I read it. I think I read it about there were some experiments on testing the intelligence of octopuses, and they had a little thing that it had to pull a chain and then open a door and get food out. And this octopus was thinking, I'm getting fed up with this thing. And so it yanked the chain, and it came right off. And then it rose to the top and started squirting all the people in their white coats. So I thought that was pretty good. There's something else going on than just...
There is something going on.
Absolutely.
Now, if you weren't pressed to figure this out in some sort of a paper that you had to display in front of scientists, if you were like, you're trying to figure out, like, what do you think it is? Like, what do you think consciousness is?
Well, you see, I mean, it's going too far to think, I know what the answer is or anything like that.
Of course.
I just think that this issue of having some kind of quantum state which preserves itself up to a certain level, and the microtubules at least suggested something where you could isolate them from the outside, and the symmetry of these things is important. And there are other structures. I suspect it's not just microtubules. I suspect there are these things called clathrons. These are molecules which inhabit the synapses. And the thing about these ones is that they're incredibly symmetrical. They're like a soccer ball. You have these pentagons and hexagons, and at each vertex you've got a protein. It's called a triskelion, and they join themselves along the edges of the pattern of the soccer ball. Okay, but it's just a substance. I mean, it's made of these proteins. And what are they doing hanging around in the synapses? I don't know. But the symmetry has a key role. There's a thing called the Jahn-Teller effect in quantum mechanics, which tells you that when you have a highly symmetrical structure like that, then there can be a big gap between the lowest energy level and the next one. And there can be information in this lowest energy level, which can be shielded from the higher energy levels. So this is a sort of suggestion that some kind of quantum phenomenon is going on in a serious way. And there's a lot to understand there. I mean, synapses themselves are kind of strange things. You might think, if you were going to build a brain, why don't you just solder the wires together at the connections, you see? What are you doing having this thing with all the chemicals transferring this information from one side to the other? I don't know, but it's something very needed by the system, and it's all tied up with these clathrons there and cytoskeleton structures, which microtubules are one of the main constituents. So you see, I don't know. There's a lot to learn, I'm sure.
So it seems like there's a bunch of different factors. There's the biological understanding of the brain itself, and then there's the understanding of the actual nature of cells and of reality itself, this is being more illuminated by science with every new discovery, and we're getting a better understanding, deeper and deeper, as to the very nature of matter and of these structures themselves.
I think it is getting deep into the way the physical world operates and things that we don't understand about it just yet. Yes. I mean, the biology is one side of it. And coming as an outsider, I get struck by certain things. I mean, quite familiar with the fact that the right side of the cerebellum controls the left hand, and the left hand the right hand. Mm-hmm. But then you look at this, and it's not just that. What about the soles of your feet, right at the top? What about your eyes, the signals right at the back? Mm. You'd think this is the most ridiculous construction. You've gone to the worst possible place.
Yes.
There must be a reason. And the cerebellum is different. Because cerebellum, it's the left side controls the left side, and the right side the right side. So there's something going on which involves these signals having to cross each other, or whatever it is. I don't know.
Well, we'd like to think that there's a reason, but then we look at other biological life forms and they look kind of preposterous, like a platypus, for instance. You look at that and you go, what is that? Is that an experiment? Is that a prototype that just ran wild?
Goodness knows.
Yeah,
well, I guess you've got to think of it in terms of natural selection of some sort.
Yes.
And I guess the circumstances there, I don't know.
Yeah.
In Australia, wherever you find it must be specific. Well, I guess a lot of that was because they were isolated from the rest of the. So you get sort of strange animals in Australia and in New Zealand where a lot of isolation from the rest of the evolution. So they did their own thing there.
Yeah, marsupials.
Yes.
Yeah.
It's just intriguing, isn't it?
Well, the phrase quantum is another one that's fraught with woo.
Indeed.
Right? And some people, like Deepak Chopra and the like, they love to use that word because as soon as you use that word, you can kind of get away with almost anything afterwards.
That's right. Yes, I have to say quantum mechanics is a strange thing, and I sort of blame it for certain things. I don't want to be unfair here. I'm not saying when I say I blame it, it gives some people the impression, okay, the fact your theory doesn't make any sense, there's nothing against it. You can say crazy things. Quantum mechanics is crazy, so why don't you accept some other crazy theory? Of course, quantum mechanics has the virtue that it does agree with an awful lot of experiments and gives you huge insights into things that one didn't have before. So just the fact that it's crazy isn't enough to to make it something you should study seriously.
Well, it's very, very difficult to understand, even for people who study it.
Yes, indeed.
So for someone like myself, I'm trying to pay attention to this without devoting my entire life to it.
Yeah.
And it becomes a big problem because there's...
There are two, in one of my books, I tried to explain there are actually two mysteries in quantum mechanics, and they get muddled. One of them is the whole subject is pretty crazy, yes. But it's coherent, and it makes sense, and if you study it properly and you say, okay, that makes sense. And this includes things like non-local effects, where you can have two things now even thousands of kilometers apart, and you can see these quantum entanglement effects. So they're still, in some sense, connected with each other, even though they're that far apart, which is pretty amazing.
That's baffling.
That's baffling, but that's part of the comprehensible part of quantum mechanics. It's muddied up because there's the other part, which has to do with this collapse of the wave function. And standard quantum mechanics really doesn't make sense. But people get them muddled, in my view. You think because this doesn't make sense and that doesn't make, well, it's all a bit crazy, and so anything crazy is up for grabs. But it seems to me that quantum mechanics, the things which are crazy and they do hang together and the theory works and you understand that, that's fine. But the things which involve the collapse of the wave function, that's not fine because we don't have the right theory yet. That's why. It doesn't make logical sense because it's not the right theory yet. That's my view. I mean, I'm a minority in saying this. Most people who study the foundations of quantum mechanics say, well, we haven't got the right interpretation yet. We have to think what it means and so on. They don't think, well, maybe it's not quite right. Maybe there's something, when these effects get big enough, something else comes in and we need a new insight, a new theory. So that's what I think.
Now, in something like superposition, where something can be both still and in motion at the same time, as soon as you say that to the common person like myself, my brain glazes over and my eyebrows raise up and I go, okay, what is... And then you're talking about entanglement, things hundreds of thousands of kilometers apart that are somehow or another interacting with each other in a way that we don't totally understand, or we don't have a theory that absolutely explains in a concrete way.
Well, it does as long as you don't get to the measurement issue.
The measurement.
The entanglement part is pretty well understood.
But the measurement
is the measurement part is not. You see, the puzzles about the entanglement is when you come to the measurement. You make a measurement over here and a measurement over there, and they can be, well, now 1,000 kilometers apart.
Right.
The record was only 143 or something a little while ago.
Wow.
But it's a long time, a long distance. But there's hardly any movement of material. So the thing that... See, in the scheme I have, which involves the collapse of the wave function, involves a certain amount of displacement of mass. Now, if it's just photons, that's light, and these experiments tend to be just light, then there's no mass displacement in the state. And so, sure, what quantum mechanics says is fine by me. Okay, it's hard to get your mind around, and I certainly agree with that. But it's logical. What's not logical comes apart about when you worry about the measurement issue and the collapse of the wave function, and poor old Schrödinger was very upset by this, quite right. Yes.
Now, when you discuss consciousness and the mystery of consciousness, and then you take into account some of these characteristics that are being displayed in the quantum world? Do you think that perhaps some of them are interchangeable or similar to consciousness itself, that there is some sort of a connection that human beings share and some strange, unique, and not understood way yet?
I think one has to be careful about these things, and sometimes do. Well, even Niels Bohr, who is one of the founders of these ideas, and sort of he tried to make a philosophy out of quantum mechanics and complementarity and so on. I think that's going a bit far. I don't really see.
Because there's no evidence for it as of yet.
I don't think so. I think it's a bit misleading. You can see analogies between things, but I don't see from myself that it should be taken much further than that. But maybe there's more there.
But you're open to the possibility should new information be.
Yeah. I mean, if it comes to things like when people talk about entanglements and things, quantum states can spread to long distances. Does that mean that human beings' minds can stretch to long distances and so on? So these people will raise questions like that. I don't think so myself. I think that's pretty far-fetched. But you might worry, well, okay, could it be that there is some quantum state which is shared between different individuals? It's hard to see that could be unless they were, if they were identical twins, I suppose they were once one cell at one time. But you'd have to preserve that information all the way through, and I just don't see how that could happen. So I'm not a fan of trying to use quantum ideas sort of directly in, say, human behavior or something. I think those analogies are pretty far-fetched, partly because the sort of mathematics you use in quantum mechanics is very specific to quantum mechanics and doesn't really apply to macroscopic behavior as far as I can see.
Is this something that is that you're asked about most often?
You mean in my research altogether, or
just amongst common people like myself?
It's only one of them. But you see, it's slightly misleading when you're thinking about what my interests are. Because I had this, as I say, I explained more or less the history of my ideas there, and I did write a book, or at least another one after that too. In fact, I guess I've written 3 books about that, although one was taken down lectures and so on. But it's not what I do mainly.
Right.
My main research is on cosmology. There's this area called twistor theory. I won't necessarily go into that, but it's meant to be foundational foundational physics, not necessarily, but general relativity. I mean, I guess the work I did originally was people paid attention to is in general relativity and black holes, what a black hole is, why we have the idea that they're there at all, that sort of thing. I worked on that at one point.
Cosmology as a whole is one of the most terrifying concepts to me, because when I start thinking about the size and scale of everything, I get to a certain point and my brain just shuts off. There's not enough juice.
Well, it's pretty huge. One has to think on a pretty huge scale. But it's like so many things. It looks sort of mind-boggling at first, and then when you get used to the idea, you can sort of play around with the ideas and maybe forget how mind-boggling it should be.
I was watching a documentary on supermassive black holes, and they were discussing how the size of this was, I don't know if this is still a current theory. This documentary was a few years old, but they were saying that there's a supermassive black hole inside of every galaxy that's 1/2 of 1% of the mass of the entire galaxy, and that one of the theories was that inside these supermassive black holes could be an entirely different universe with hundreds of billions of galaxies, each with their own black holes, and then it's infinite.
Well, you see, I have an idea which I think the mainstream does still regard as a bit crazy, but not like that. I don't think you're going to have much fun inside a black hole.
No parties in there?
Not much. Well, you could have a really big black hole, and there's a lot of time in there. A really big one. If you were in a spaceship, you could have a few parties before you went to singularity. Yes, but I'm not sure I recommend it. I mean, black holes are remarkable enough, but I mean, the thing I did, which was in 64 and published in 65, was to show that black holes, well, I'm using a terminology that wasn't around at that time, that the black holes, gravitational collapse. You see, the history went back to, originally, I guess, Chandrasekhar, an Indian scientist, when he was not quite 20, I think. I can't remember if it was 19 or 20. And he was going to England to study physics, astronomy, and so on. And he worked on this problem about what holds white dwarfs apart. These are these very massive stars. The companion of Sirius is a white dwarf. And he was doing calculations to find out whether they... what the interior is a very particular structure of matter. And he came to the conclusion that if they had a bigger mass than a certain amount, which is about a bit less than 1.5 times the sun's mass, they wouldn't be able to hold themselves apart. And so they would collapse. And he didn't speculate on what had happened. He just won his last... There was some very modest comment he made, is one, we are left speculating on possibilities or something. But then that was in the 1930s, I guess, around about 1930. And much later, just before the war, Second World War, 1939, well, I say a bit later, I guess, 1939, there was a paper by Oppenheimer of atomic bomb fame, and Schneider, which is a student of his, Hartland Schneider, and they produced a model which was a solution of the Einstein equations, which describes a cloud of dust which collapses and becomes what we now call a black hole. So this was the first clear picture of collapse to a black hole. Now, in their picture, they made two huge assumptions. Well, one of them is dust. The material, that means it didn't have any pressure, and so you could imagine when it gets close to itself, it might push away if it had pressure in it in any way, but this was just dust. That was one thing, but more important, that the model was exactly symmetrical. So it was just spherically symmetrical. All the matter falling in, the dust particles would be focused right into the central point. And so it's not so hard to believe that you get a singularity where the density goes infinite, the curvatures go infinite, and your equations go crazy. So at that point, when the dust reaches the middle point, okay, it's not so surprising because it's a very contrived situation. So I think a lot of people thought, well, perhaps we shouldn't take it seriously. I think they weren't sure. But then there was a paper by two Russians called Lifshitz and Khalatnikov, and they seem to have proved that you didn't get singularities in the general case, that somehow it would swirl around and swish out again, you see. So that was the possibility. And then there was this discovery, I think in 1962, when Martin Schmidt, a Dutch astronomer, Dutch-American, I think where he was living there at the time, I don't remember, but he observed what became what we call the first quasar. So this was an object which was irradiating an awful amount of energy, far more than an entire galaxy, but it seemed to be a very small thing. It couldn't be much bigger than the size of the solar system, if even that big, because variations in brightness indicated that the speed of light the size of it had to be comparable with the speed at which the variations in brightness came about. So it seemed to be an object that was enormously energetic, producing more energy than the whole galaxy, and varying with such a degree that it must be fairly small. And this raised the question of whether it was small enough to be what we now call a black hole. In other words, there's a thing called the Schwarzschild radius. Schwarzschild was the man who first discovered the solutions of Einstein's equations, which described this spherical body. But he didn't extrapolate it inwards to what's called this horizon. We call it a horizon now. It used to be called the Schwarzschild singularity. And people began to realize that it wasn't really a singularity. It's more something you could imagine falling through. I guess it was Lemaitre who first made that clear. But not many people paid attention. But that was the idea of the black hole. And it looked then as that these quasars could be having some black hole in the middle of them. And I remember John Wheeler, who was at Princeton then, very distinguished scientist, and he got very worried about these things, and he talked to me, and he was worried about it. And do we believe, is there a singularity in the middle? Do we believe Lifshitz and Klatnikov, that they sort of swirl around and bounce out? What are we supposed to think? So I started thinking about this problem, and since at that time, well, you see, either people, when you want to solve the Einstein equations, either you make a lot of assumptions and it's symmetrical, like the Oppenheimer-Snyder model. You assume it's got very special properties, and then you can maybe solve the equations. But only very, very special cases. And the computers weren't powerful enough to tell you very much about what happened. So I started thinking about this problem and realizing that I'd have to think about it in a different way. And so I used ideas which involve ideas from topology and things like that to show that there had to be a singularity in the middle, provided that collapse had reached a certain point of no return. I guess to get some idea of it, I don't know, it's not too misleading. There's a mathematical theorem called the hairy dog theorem.
Hairy dog theorem.
Yes. I mean, that's just a jocular terminology.
Right.
But you think of something which is topologically a sphere. That means, you see, you imagine a dog shape, but you could sort of move it around with a piece of plasticine until it looked like a sphere. It doesn't have holes in it. Okay, forget about its digestive system, you see. You're thinking about the surface outside. Mm-hmm. And then the problem is you try to comb the hair on the dog all the way around, and the theorem says there's got to be somewhere where the hair doesn't lie flat. And you try it on a sphere, there's got to be a point where the hair makes a kind of singular point. So it's a bit like that. You have no idea where the singularity is, but you know from general topological reasons that there's got to be one somewhere. And that was the sort of argument that I produced. And I guess a lot of people had a little bit of trouble because they'd never seen this kind of argument. And a lot of people picked up on it, in particular Stephen Hawking. And it became, for a while, many people working on it. I guess it's not so popular now because probably we've run out of theorems.
The idea of a singularity, is when you see something like a quasar or the center of a galaxy, mm-hmm. And we were talking about a black hole. When you say a singularity, what exactly do you mean by that? Well,
the normal expectation is that you have a place, like in the middle of the Oppenheimer-Snyder dust cloud, a point there where the density becomes infinite. And so the curvature of space-time becomes infinite. So you have a place where the equations run away and they go to infinity, and you say, well, something's gone wrong. But maybe initially it was in these very symmetrical cases. But what you could show by these indirect arguments that somewhere something's got to go wrong. You can't continue the equations of Einstein and they got stuck. Right. To the place where they go infinite, or what in detail happens, the theorems don't tell you. They just say that something goes wrong, and that's what we call a singularity.
And if a black hole is larger or smaller, the singularity remains constant?
It remains in there.
It remains in there, but it's not measurable in terms of its actual size?
I don't know whether you can measure its size very well, because its size, that's an intriguing question. You might say the size has gone to zero, right. But it could be quite complicated and irregular, not like the original Oppenheimer-Snyder one, which is all just even then a point is the wrong point of view, but let's not go into that. No, there is something about the structure of these things you can say. They're not all the same, no.
Then the singularities are not all the same, but the black holes are not all the same.
They're not all the same, but that's one of the strange things about black holes, is that if you let them settle down, they're not all the same to begin with, but there are not many different things they can settle into. They can have rotation, they can have a certain mass, and the mass translates into the size of the diameter of the hole, and you've also got rotation, so they can rotate. And these are, Schwarzschild found the non-rotating ones, and it was Roy Kerr, an Australian, who first produced the solution for a rotating black hole.
Rotating?
Yes, a rotating one. But then you see the remarkable thing is that's what they settle down to. So there are good theorems which tell you that a general black hole, which is very complicated, fairly rapidly will settle down and become one of these Kerr solutions, the rotating black hole.
I remember when I first saw that documentary, and I saw when they were discussing the shape of these galaxies, and that the center of it had this supermassive black hole that was slowly devouring the galaxy.
Yeah.
I mean, it is an unbelievably beautiful yet simultaneously terrifying idea. Is that there's this infinite power in the center of infinite mass that's absorbing slowly but surely everything around it.
Yes, well, it's not infinite mass. The mass is quite well defined, and it's not infinite. But it's a good question. I mean, if you wait forever, how much of the mass actually gets swallowed by the black hole? You see, I think the picture is to think not just of one galaxy, but a cluster. You see, our galaxy has this 4 million solar mass black hole, and we are on a collision course with the Andromeda galaxy. And I don't know how long, but some time in the future. Yes, the black holes will probably spiral into each other, and there'll be one big one.
So it's definable mass, but in infinite density, and that this point, where they were speculating that this could possibly, in the center of these supermassive black holes, if you could go through that, there would be another universe.
Well,
you see, that's total nice speculation.
It's a nice romantic thought.
It's more woo. Is it more woo?
I'm afraid so.
Sounds so good, though.
Yes, I know. Well, it's a shame for science fiction because it makes a nice.
It's interesting that we try to make things more complicated than they are because they're so complicated as it is. It's like dark matter, for instance. It boggles the mind that we don't really totally understand 90+%.
Well, that's a good question.
Yeah, what is that stuff?
Well, you want me to tell you my theory here?
Yes, please.
Well, you see, it's part of a story which, I don't know, about 15 years ago, I must have, years are passing by, I can't remember how long ago now. So I had this idea. You see, the universe as a whole is expanding. Now, early in this century, don't ask me dates again, some people, by observing supernova stars, exploding stars, very, very far away, they found out that the universe is actually accelerating in its expansion. And some people found this very mysterious. On the other hand, it's in all the cosmology books because there is that expectation. You see, in 1915, Einstein produced his general theory. In 1917, he introduced what's called the cosmological constant. So you think of it was called lambda. You think of a V shape turned upside down, which is a lambda. And he introduced this term for the wrong reason, because at that time, there was some indication the universe was expanding, but not very clear, and Einstein, I guess, maybe didn't know or didn't believe it, and the Hubble's observations hadn't yet come to make a convincing case of the expansion. So Einstein thought, well, maybe the universe is static. It's kind of philosophically nice to think that it's sitting there all the time. And he couldn't make it do that, so he had to introduce this term called the cosmological constant. And he did that, and then very much longer after this, Hubble showed that the universe does seem to be expanding. And Einstein regarded this lambda term as his biggest blunder, which is an irony, because it turns out that this term is probably the explanation for the expansion of the universe that we now see. So it's what people call dark energy. I don't like the term very much because it's neither dark nor proper energy in any clear sense, but still, let's not worry about that. Right.
It's an odd term.
Yes, I think so. It's all a little confusing because there's dark matter as well, which is quite different. You mustn't get them confused. But the dark energy, as it's called, or the cosmological constant, which, as far as we can tell, is completely consistent with the observations. It's a positive number, very small, but seems to be producing this expansion. And I'm quite happy with that viewpoint because it leads to a picture which I've been trying to plug for a while now. Maybe up to 15 years, I can't remember. The idea, it's hard to explain, but let me try. It came about because I was worrying about the remote future. And I was thinking, okay, when these black holes are around, they swallowed up all the stars and they're just sitting around. And what's the most next exciting thing happening? Well, the Hawking evaporation. They're going to radiate away. Stephen Hawking showed that black holes had this temperature, extremely cold. I mean, these enormous ones are absurdly cold, much colder than anything made on the Earth. And but when the universe expands and expands and expands, it gets colder than the black holes. And so those black holes become the hottest things around, and so they radiate away very, very slowly, this Hawking radiation. And that carries energy, and so they shrink, and they shrink, and they shrink. And finally, they disappear with a pop. When I say pop, it's probably a pretty big explosion, but not that big from the cosmological, astrophysical scale. So they disappear. Well, it may have been pretty boring when you're sitting around waiting for the black hole to go pop, but afterwards that's really boring. So this was the picture I thought of, being rather depressed by it, thinking that's the fate. You see, the fate of all the interesting things happening, ultimate fate, is this unbelievably boring final state. Okay, this is an emotional argument, but give me a bit of leeway.
Okay.
So I began to think, well, it's not going to be us who are going to be bored, because we're not going to be around. But the main things that will be around will be photons. And it's pretty hard to bore a photon for two very good reasons. One is it probably doesn't have conscious experiences, now that's sure. So, but the other is more the science point, that they don't measure time, because a photon has no mass. It travels at the speed of light. And the way relativity works, it means that clocks stop, if you like. So if it had experiences, the moment of its creation would be one moment, and the next moment would be infinity. And so they just zip out to infinity without noticing a thing. Now, you see, I'd been doing work on this kind of thing, thinking more about gravitational radiation and how you measure its energy and things like that. And it was a very useful picture to squash down infinity. A useful thing to think about here, if you've seen these pictures by the Dutch artist M.C. Escher.
Yes.
And there are those which are called circle limits. And there's a very famous one with angels and devils interlocking, and they get all crowded up onto the edge. Now, what you've got to think about is that this is a kind of geometry called hyperbolic geometry. And the angels and devils live in that geometry. And the ones right close to the edge think they're the same size and same shape as the ones in the middle. Oh,
there
you got
right
it.
There.
Great.
Yeah.
And so the idea is that if you look at it from the angels and devils' point of view, that's infinity, that boundary.
Mm-hmm.
But from our point of view, we can look at it and we have what's called a conformal map. That picture is a conformal map. What that means is that little shapes are quite consistently drawn, but they can be big or small. And you don't care about whether they're big or they're small, as long as small shapes are accurate, or angles, if you like, are correctly drawn. So it's what's called a conformal map, and that conformal map describes infinity. Now, you can do the same thing to the universe. When I say do it, I mean you can imagine it, where this remote future, you can squash it down, just like in the Escher picture, to a finite boundary. And as far as the things with no mass, they don't have a way of measuring how big or small it is. The Maxwell equations don't know the scale if they don't care. It's work just as well for small as for big, and you can stretch it in some place and squash it somewhere else, as long as the stretching and squashing is isotropic, so just as much one way as the other way, which means more or less that you keep what I call the light cones there. Let's not go into details here, but it means that if you have things without mass, and most particularly the photons, then that boundary is just like anywhere else, and the photons go zipping up to it, and so you might think they've got to have somewhere to go. Okay, well, you don't have to think that, but that was the point of view I had, that the photons need somewhere to enter, in a way. But then, where does it go? But then there's the other picture, which is the opposite end. There's the Big Bang. Now you can do a similar sort of trick there, which is stretching it out and making it into a boundary. And that can be done too. I played around with these ideas for a long time, and the standard cosmology models you can do it with. But the more complicated cosmology models, you might have one which is very complicated Big Bang. The general ones don't look like that at all. So you need a condition which tells you that the Big Bang was the very special kind that it was. It's all tied up with this thing called the second law of thermodynamics, and it all ties together with physics in a way which perhaps we don't have time to talk about. But it seemed to me a really good idea to have the condition on the Big Bang that you could continue it in the same way. I should say the idea of doing this was a former student of mine, Paul Todd, who was a colleague of mine, and he used this as conformal continuation as a nice way of saying what the condition is on the Big Bang to give you what you want. But that's a huge condition. But nevertheless, it's what starts our universe off in a very special state, which is what we live off in a way. It's the second law of thermodynamics needs that to get going. Anyway, I don't know if you want to worry about that. But anyway, the point was that it looks as though it's a good condition on the Big Bang, but it also should be conformally like a boundary, which if you had no mass, you wouldn't notice it. Okay, you've got particles with mass running around near the Big Bang, but as you get closer and closer and closer, the energy goes up, the temperature goes zooming up. They're zipping around at such a speed that the energy of their motion is much bigger than the E equals mc squared mass, Einstein's mass. The energy in the mass is a certain amount, but when they get so hot, you can forget about the mass. So they, like photons, behave like particles without mass, and so they're just interested in conformal geometry. So the crazy idea I had, not just only you stretch out the Big Bang and you squash down the infinity, but maybe our Big Bang was a squashed down infinity of a previous eon. So I'm saying our eon began with the Big Bang, ended up with this exponential expansion. There was another one before us. There will be another one after us. There was another one before that, and so on.
So it's an infinite cycle of Big Bangs.
That's the picture.
And constant expansion to the point where there's no more energy, and then somehow or another a Big Bang comes out of that again?
Yes, that's right. Well, that's the tricky part that people have trouble with.
It's universally accepted that the Big Bang was an event. There's no
pretty well
conflicting theories that are attractive?
I would say nothing terribly popular. There are certain ideas which say you can continue into before the Big Bang. Paul Steinhardt and
what do they think that was?
It has things in common with my model, but it's not quite the same. And you see, it's still. You see, there was not long after Einstein produced his theory, and this Alexander Friedman, who was a Russian mathematical physicist, and he produced the first cosmology models. And one of these was one which has sort of bounces. A Big Bang, it expands out and then it contracts again. And then it bounces and contracts. And so that was one of his models. The only trouble is if you put irregularities into these models, you get black holes, and these black holes form an incredible mess at the end, and that doesn't join on to a nice smooth Big Bang of the next one. So you have trouble with those models. But still, people take these things seriously. And as I say, Steinhardt and Turok have a model which is like that. So these are things one has to think about. My own view is that they don't take into account the black hole problem, which is that my one gets rid of that because the black holes all evaporate away by Hawking evaporation. And so it forms a model. I used to give talks about this, feeling quite happy nobody would ever prove it wrong, so I can go on talking away at it. But no, I wasn't quite happy with that. I thought maybe you could see signals coming through. So I had one idea about that. But more recently, and this is only just this year, I have two Polish colleagues. That's Krzysztof Meissner and Paweł Nierowski. And there is a Korean who works in New York called Daniel An. And we, the four of us, have a paper which I think today or tomorrow will be the new improved version of this paper, should be on the archive. And the title of the paper is, Are We Seeing Hawking Points in the CMB Sky? Now, what's a Hawking point? You see, I talked about the black holes. See, in the previous eon to ours, assuming it's more or less like ours, there would be black holes in clusters of galaxies, huge, enormous ones, swallowing up pretty well the whole cluster. And what happens to the energy in those black holes? Well, it goes out in Hawking irradiation. It takes an age, ages and ages and ages, maybe 10 to 100 year Google years or something, ages and ages. But all that energy in the picture comes out basically in one point. Think of that Escher picture, and right at the very edge, you see there are an awful lot of angels and devils squashed together there, so that the entire radiation from that single black hole will be squashed into that little point. Now we're on the other side. What do we see? Well, there will be a big release of energy at that point, and that's what we call the Hawking point. And it spreads out. You see, what we see in the cosmic microwave background, this is radiation coming from all directions, and this radiation doesn't come from the Big Bang exactly. It comes from 380,000 years after the Big Bang. So there's a sort of last scattering surface where photons, which are trying to get out, finally can escape, and we see them. Now, that spread out from the Hawking point to what you see in the cosmic microwave background, in the last scattering surface, is something of the diameter of about 8 times the diameter of the moon. No bigger, no smaller. Now, you wouldn't see the whole thing because our past cone, what we see, to cut across it, we don't see the whole thing. But we see probably most of it. So you could imagine something from about 4 to 8 times the moon's diameter, which is a small region which is highly energetic, more energetic in the middle, and it tapers off as you go to the edge. And we seem to see these things. The analysis that the poles, they have the techniques, and the actual analyzing the data, this is the Planck satellite data, was done by Daniel Ann. And then we look at the data and we seem to see an effect, which, see, what you do is we've got only one universe, that's what they complain about, so how do you know if something's real or not? Well, you make zillions of fake universes and you compare this with them. There's a lot of technique about how you do this. But Daniel first did 1,000 of these fakes, and there were sort of 2 sizes of these. You look at these rings to see whether the temperature goes out from the outside to the middle. And there were 2 sizes, both within this size that I say, about 4 degrees across the sky. And there was no evidence of them at all in the simulations. So this is a real effect. Okay, then people were skeptical of this for one reason or another. So Daniel did another, 10,000 altogether. And occasionally there are 1 or 2 which do, 2 or 3 to be precise, where you see this effect in the simulations. But if you work out the probability that this is a real effect, you come up with a confidence level of 99.98% that this is a real effect. So we're waiting to see what people say about this.
What are your thoughts on multiverses?
Well, you see, this is different because this is what's sequential.
Yeah.
So I don't call it a multiverse. They each influence the next one, and so they're not independent worlds.
Right, but the possibility of independent...
Yeah. Well, you see, there are 2 reasons for believing in multiverses. One of them is the quantum reason, that maybe where you have the Schrodinger's dead cat and the live cat, they're in different worlds and they're separate universes. I don't believe that argument. I don't think that's the right way to look at quantum mechanics, but many people do. And that suggests that you might have these multiple universes in some sense.
What's unattractive about that to you?
It doesn't explain what we see. So you want a theory which explains the world we see. And the world we see, you get collapse. The state does. And to explain that, well, it's only because we've drifted off into some world and another version of ourselves has drifted into another one, and some see one and the others see the other, and they're all in superposition. It doesn't explain why you see one world. And it just has this kind of coherence. I mean, lots of people try, and there are many attempts at this sort of thing. It's quite a widely held view. And if you believe quantum mechanics, that the collapse is not real, and it doesn't happen, and all the alternatives, the dead cat and the live cat, coexist in different worlds, that's the interpretation. That's a view. I don't think that. I want an explanation for the world we live in. And you don't see cats, different worlds with cats and... Well, it's a long story.
Right.
I mean, it's clearly a view you can hold to, and if you don't want to monkey with quantum mechanics, it's where you're led. So that's right. That's the alternative. Either you don't make a single try to change quantum mechanics at all, and then you are led to this multi-world, many-world picture. I think it even doesn't make that much sense, so you've got to be careful about it. That whether they are really like different, distinct worlds, I don't think it really... My view is it doesn't really work. But let me not try and attack that. I think I have a different view, which is that the theory is not quite right, and that there is something which makes the collapse into a physical process. And there's only one world. Now, the other many worlds view, which comes from a different reason, and that is that there seem to be various accidents maybe one of them being that the neutron is just slightly more massive than the proton. That's one. There are lots of other accidents we see that if they were a little different, then life as we know it couldn't happen. And so how do you explain this? Well, some people say, well, all these universes with different values of these constants all coexist. It's just we only see the one that we're in because the numbers come out right for us. So that's what's called an anthropic argument. Okay, I can see the argument. I don't like it much. It's sort of, I think we need a better explanation for why the numbers are what we see and so on. But that one makes more sense to me than the other one. So I think one maybe has to take that seriously. But it's certainly not the view I'm presenting here with this picture.
For someone like me, it's so interesting to know that there's still a considerable amount of speculation.
Yes. Oh, yeah. Well, there's a lot of speculation, but a lot of it is pretty off the wall, and a lot of people think mine are off the wall. You see,
right? Well, who's to say?
Okay, I'm an old man now, and so did decent things in the past, but you shouldn't trust his views now. You see, so I guess that's what people think. I don't know, but you see, if it was just me, I could understand that view. Right. But I've got these Polish, and I've got an Armenian colleague who's done things on this too, and it can't be that we're all off the rails, I think.
No, it can't be.
There's something out there, and now with the Hawking points, there's something people can really go out and look for. And if they don't see them, there's something funny going on somewhere. If they do see them, there's something else going funny on, which they'll have to think of another explanation. Unless it's my explanation, they'll have to think of a different view from the current inflation view, which is in real trouble with these observations as far as I can see.
Do you anticipate in any foreseeable time in the future a better understanding of dark matter and dark energy, or perhaps a better definition of what those things are?
Yeah. Well, you see, I think my own current view is that dark energy, as it's called, is the cosmological constant. Now, that's not an explanation, if you like, because why has it got the value it has? Why is it there at all? And there are certainly questions about that, which I agree with. Dark matter, I didn't go into this, but in this scheme of mine, it has to be there. When I say it, I mean that if you want the equations to make sense, which cross over from our remote future to the Big Bang of the next eon, you have to have a creation of a dominant new material, which is scalar. As I say, it doesn't spin, it's just ordinary particles, and that they only interact gravitationally. And that's what we see. But the theory that I'm putting forward would make these things very massive. They're about what's called the Planck Mass. I don't know exactly because there's some freedom in this. Something like the Planck Mass, which people describe as the mass of a flea's eye. Don't quite know why they make it. But that's about 10 to the minus 5 grams. So you're looking at a 100,000th of a gram. So it's sort of an appreciable size. It's not, it's not like basic particles in physics.
It's measurable.
It's the sort of measurable thing you could imagine you could get hold of in some way. But that's huge for a fundamental particle. So it's a wild idea from that point of view. But also they should decay. And they should decay into gravitational signals, which maybe could be seen by LIGO, maybe have been seen by LIGO, and thrown in the rubbish bin, because there'd be different types of signals from what people would expect. I wouldn't like to put my money anywhere there, but I'm hoping that these dark matter particles are the ones that come from the theory that I'm putting forward. So that would be another consequence of this particular point of view.
And they've observed, correct me if I'm wrong, entire galaxies that they believe that consist of dark matter.
Let me see if I remember what it is. There are some galaxies the other way around which don't seem to have any dark matter. It's puzzling. There are other galaxies which have huge amounts. That's probably what you're referring to. Whether they were only dark matter, you'd have trouble seeing them.
Right.
Because dark matter, after all.
It was just a measured thing,
yes.
right?
It may be. I don't know that one. It's quite possible. Yeah, I don't see why not. They just have to have some reason why they clump together in this way. You see, it's quite possible if galaxies collide, then when you see the stars tend to go through, so they'd accompany the dark matter. The dust in the galaxies tends to get stuck and stay where it is. So if two collide, then you'd have a big pile of dust in the middle. But I think the dark matter tends to carry on through with the stars. I don't know. There may be some process which could produce just islands of dark matter. I don't know.
When you discuss the cosmos, maybe the single most intriguing possibility to us as human beings is what other intelligent life, if any, is out there. And how interesting is that to you? Because you spend so much time studying the fundamental particles of the universe itself. How interested are you in the possibility of other intelligent life forms? Or have you just like put that out into it's just so ridiculously unlikely or so far away from us that we're probably never going to make contact?
Well, you see, it's not so. There's this SETI program where they're looking at to see whether they can see signals from distant civilizations. The problem there, from my perspective, is that although they might be out there, they've got to have had a real head start on us before you would see them. Of course, they might have done so, but then I don't know. You see, actually, Vahe Gurzajan, who's my Armenian colleague, and who looked also for these ring-shaped things, and looked at them in a different way from the Polish people. But we seem to have seen something there. But we wrote a paper in which we speculated on beings from the previous eon communicating with us. And the advantage there is that you're looking at the really advanced civilizations,
really
right at the very end, you
from
see.
Billions of years ago, that their universe disappeared and then had to come back to a Big Bang state
the
again.
signals could come through, yes.
And somehow or another, those signals remain.
It's conceivable. I agree it's pretty far-fetched, but, who knows what...
So eons, how many billions of years are you talking about? Like the Big Bang was 14 billion?
Yes. But you see, that's way at the beginning, in a sense, or it's three-quarters of the way through in another sense. It depends how you draw the pictures.
Right.
In the sense of interestingness, or in the conformal picture, we are already three-quarters of the way through.
So 14 billion to now, so we have how many billion left? You
can't count it as years, you see. The trouble is it's a cheat.
It's a cheat.
The year count is as much as you like. It depends on something else. The mass has to fade out, and how you measure time becomes problematic. And it's either infinity, you see, which isn't much use, or you might have a different definitions of time, which depend on what particle you're using as your clocks and things like that.
So are you essentially saying that it's entirely possible that we are the furthest in terms of our technological achievement and our understanding of the universe itself? It's possible that we're at the front of the line, that there might be some other intelligent life forms in the universe, but they might be behind us.
Well, there would have been... I'm not saying they got through, you see. Well, maybe they have techniques for getting through, but that's a bit hard to imagine. But maybe information from them could get through, and maybe
you mean from the previous eon?
Yes.
Oh, they might have got through, like somehow or another survived.
Yes, but it would have to be in the form of photons or something. Yeah, no, you could. It's not. I'm talking about ridiculous speculation.
Sure,
now.
but encoding information into photons.
Yes.
Wow.
It's conceivable.
Sure.
Now, I don't want to say that I see it happening or anything, but it's not out of the question that they could develop some technology which would get information, which might be them in some sense, across in the form of photons.
But you're not optimistic about current intelligent life somewhere in the universe?
Not too optimistic, just because, well, maybe it took us a long time to get going because the dinosaurs were there for a while and somebody might have got in there earlier in their different planet and they could have got there quite ahead of us. It's conceivable. I'm not going to rule it out. I'm just not terribly optimistic about it. No, I think it's worth doing. It's worth looking.
Yes, but it's not something that you're really curious about.
I'm expecting. It's not so much. I'd be curious certainly, but I'm not expecting it, I guess.
Is it just because of the overall lack of real evidence, and it's just not an attractive thing for you to pursue?
It's quite attractive.
It certainly would be. I don't know.
I've just been doing other things, and I don't know. There's enough to do in the world. I haven't really come to terms with it very hugely. So I know there's this activity, and I'd be interested to see if any kind of, if there was this thing that came past that some people speculated was sent there by a different intelligence, which came quite close in our solar system.
Oh, that was that strange-looking cigar-shaped.
Yes, that's right.
Yeah.
I mean, I don't see any real reason to believe it's an alien spaceship.
Was it because of the way it was traveling? That was the idea?
It was something.
Something curious about it?
Serious people did suggest it might be something sent by an alien civilization. Well, it's worth, if one could connect with it in some way. But I don't know. I guess it's too far away now.
Well, it's another thing that's so uniquely fascinating for us, the concept of another life form out there.
Oh, sure. Yes. No, you see, there are lots of things I'm interested in. The ones I talked to you about are perhaps some of the main ones. Although the consciousness one is, I'm glad that there are people doing it. And you see, this is one of the things. There's this institute that's being created using my name, and James Tagg is involved with this, started it. And I was I was a bit worried about having my name attached to this thing when I didn't know much about it. But it seems to me a really important thing where you can, the deliberate purpose of it is to develop ideas which make sense but are not mainstream. And one of these was the consciousness thing. So, Stuart Hameroff is doing it, but it's not a activity that's being taken part, people researching it in detail in other parts of the world. So to have a place which supports that kind of thing is great, and I think that's very good. But when I heard about it first, I thought, well, most of my interests are on the physics side and not so much in biology, which I'm pretty ignorant about. And there are lots of ideas on that side, not just the cosmology, but ideas and building experiments which might detect the collapse of the wave function. And one idea is to look at Bose-Einstein Condensates. See, I have a colleague that's Yvette Fuentes, who I knew about and who had these ideas of how to use Bose-Einstein Condensates to detect gravitational waves. And that's also a very, not a mainstream way of looking at it, but a very clever idea. And the Bose-Einstein condensates, because it's so quantum mechanical and they're so cold, they're almost virtually absolute zero. And they can keep external disturbances from causing problems. And you can manipulate them in ways to make them in two places at once. People have done this kind of thing. And so it might well be a good way of testing the Schrödinger cat thing, whether state reduction or the collapse of the wave function is a phenomenon which is of the kind which I hope might be like gravitational effect. And in that case, if it is, then that would be relevant to the consciousness problem. So all these things tie together in various ways. And so the hope was that these things which are, could be supported. And I thought it was important because there's always the danger of such an institute being regarded as flaky because he's doing weird things. Who cares? So the important point from my perspective is that they should be things which can be and either now, immediately tested experimentally or within a few years. So they're things which are really you can get your hold on. You can get and test them and see whether they're right or not. So this would be a protection against thinking, well, these are just crazy ideas that are being pursued. They have to be ideas which are capable of test and have a reasonable chance of showing evidence in their favor or against, whichever would be interesting and important to know. So,
from the outside looking in, to me, it's so fascinating to watch intellectuals as yourself that are bouncing these ideas around that are possible but are not mainstream.
Yes.
And that it seems to me that it's a precarious sort of tightrope walk. Like, you don't want to say anything ridiculous that's not true.
That's
but
right.
You would love to say something that seems to be ridiculous but turns out to be in fact accurate and provable.
Yes.
And so there's this dance.
I absolutely agree. Yes, that's absolutely right. And of course, you've got to play with ideas which are on the sort of edge of what we know. Otherwise, you're stuck with what we know. And these things will simply get channeled down the old routes, and you need to be able to break free of those from time to time, but not in a way which is too crazy to be examined to see whether there is truth in these ideas or not.
Because of this inclination that people have to go towards woo or towards crazy ideas, it is important for the skepticism, right? It is important for the scrutiny.
Yes. Oh, absolutely.
So there's real danger in that ledge.
I agree. Well, you see, there's a strange kind of problem, you see, because with these observations, not about the Hawking points, which I was just describing, but the earlier ones about black hole collisions. And my Armenian colleague and I had written a couple of papers on this, and we hadn't got any response at all. And the Polish people, and they'd written papers, 2 of them accepted by respectable journals. And Christoph asked me, what kind of response have you got? And I said, 0. So I asked him, what about you? How about what response you got? 0. So this is kind of spooky, you see.
Right.
We've got these things out there in the literature, refereed, accepted publications. And instead of people, saying, this is a load of nonsense, look, it doesn't make any sense for this reason, and this disagrees with this observation, and so on. That was fine. If I see that, I might be unhappy with it, but you've got something to work on. You say, I see what's wrong, something needs modifying here. That doesn't explain properly. That's what's needed. Or, yes, no, you're right. I better abandon this idea. All these things come from criticisms, and to have absolutely no attention whatsoever paid to these papers is something I find spooky.
Why do you think there's no attention paid?
I don't know. I don't really know. I mean, one of the things is there's so much information and that people don't have time. They've got their own projects and they don't want to pay attention. And they think it looks crazy because it's too much outside the picture of the world that they have. And I think a lot of it's that. And they maybe say, well, look, I'm an old guy now, and maybe I did good things in the past, but maybe I've gone a bit off the rails. But I think that, I've got colleagues. It's not just me.
Right.
And these respected people who work on these things too. So I don't think that can be a complete explanation. Maybe it's part of it. But
the sheer volume of papers that are published, it's got to be impossible to keep up with all of them.
I think that's a big part of the trouble. Because there are other ideas which to me look crazy, and to other people don't look as crazy as my ideas, you see. So maybe that's why. And a lot of them have more attention paid to them than the ones we have. I'm curious to know whether the Hawking points will take off or not.
Well, I'm so happy there's people like you doing this kind of work, and then someone condensing it down to an understandable point that someone like me can absorb and just try to get a better picture of this insane reality that we're living in.
Yeah, well, it is pretty weird. You're right.
It's so weird.
Absolutely.
And it seems like the more I talk to people like yourself and the more you study this, it doesn't get less weird. It gets more weird.
Yes, I think that's right. Well, I don't know.
With more information, it seems to be more fantastic.
There's certainly a lot of very weird things, but the point about them is that they got to make sense.
Yes.
They've got to make mathematical sense. They've got to agree with observational facts. And that rules out a lot of the really weird ones.
It does, but even the ones that are observable and do adhere to the facts, they're so fantastic. It's so the reality. It's one of the things that's most frustrating about people's inclination to lean towards the woo, and I've been guilty of it myself. It's so attractive.
Yeah.
But what's frustrating about it is that provable reality is so titanically bizarre.
That's true. No, I agree.
That it's almost like, why bother with the woo? The provable reality is...
You make a very good point.
It's
Absolutely.
woo in and of itself.
You're absolutely right. No, it's very, very strange. And quantum mechanics, in so many ways, is. But you see, you've got to... I think there's a little bit of a danger of separating the things which are... Well, first of all, they could be just wrong. Secondly, there are things which do require quantum mechanics to be changed in some way. And the other ones, which are within quantum mechanics, are just weird. And that's absolutely true. There are these things which I believe have to be true, as much as the dyed-in-the-wool quantum mechanics people who follow the party lines and so on. Yeah. I mean, these quantum entanglements, the fact that things can be, whatever it is, a couple of thousand kilometers separated, and yet know each other in a way you can't explain that they're separate individuals. They behave as though they're one, what are called an entangled state. And you can make experiments which reveal that. I mean, it was John Bell, who was an Irish theoretical physicist, who really made all this very clear, that these things are real manifestations of the peculiarity of quantum mechanics and really out there in the world.
Was it J.D.S. Haldane that said the world is not only queerer than you suppose, it's queerer than you can suppose?
That's correct, he did, yes.
That's what this is, right?
Indeed.
It
Yes,
is.
it's that kind of thing. Yes.
Well, listen, sir, thank you for your time. I really appreciate it. I really appreciate talking to you, and thank you for all your work and your contribution to our understanding of what we're looking at here.
Well, I hope it helps a bit.
It helps a lot. I appreciate you very much. Thank you.
Thank you, sir.